In this video, I'll use straight away this equation. This is a weak form general equation for the K. Alright, if you don't know what I'm talking about, you should watch this video, l8v5 especially. Alright, but in order to derive this video at l8v5, you have to watch all these videos first, 5. So these 6 videos over here will give you a full understanding of what this equation is all about. Alright, but I'll not go into details because this is not my purpose over here. Alright, so I'll just simply take out this thing from that particular information that I've provided you. Okay, so if I were to do this, alright, just simply drag this all the way down. Alright, I will expand this thing. Okay, so if I were to expand this, alright, as you can see, maybe I should write it down for you. Okay, so I have integration, instead of v, I write l, I have dx. So this e over here, I'll just simply keep it e, and then we have an a, because a times dx is dv. So then simply breaking out the dv into dx and a. Alright, so far so good. And therefore you have a line integral over here. Later on I'll explain why is this line integral that is the meaning. Alright, so you have b and bt. Okay, so therefore this whole thing over here is your 1 over here. So far so good. Alright, and therefore what is line integral? So far this one is the volume integral. Now you are talking about the line integral. So the k itself, the stiffness matrix, is telling you that the integral along the line is this line over here. Just take a look. Alright, it's this line over here. It's the mixed section. Okay, so the line, if you still remember your shape functions, you have this shape like this, and you have this shape like this, right? N1 and N2. Alright, and you will multiply with U1 and U2. So therefore, if you were to mix them together at different nodes, at N1 and node 1, for example, alright, you will have something like this, right? 1. And then you're going to multiply by certain U, some magnitude of U, right? So U1, or in other words, maybe it's 3. So 3 times this one, where you have the overall section like this. So your whole shape functions for node 1 is this shape. Alright, and then for your node 2, we actually show you in the previous video, so that if this is 1, alright, you have another U2 over here, alright, which is maybe if it's 2, then you're just talking about this magnitude. And if you were to put them all together at once, you have something like this. Alright, so there will be a line, this particular line will be the line. Alright, but it's not exactly that particular line, but to some extent it influences your line. So in some of the case that happens, you have a different line because of different magnitude that you put in. You have different lines. You may have like this, you may have something like this, or you may have also getting back the same line, but maybe a slightly tuned out and things like that. So as you can see, this is different lines, and these are integration along this line, and you get to know how the beam deform. Alright, so this is just the meaning of that. And then you have to extend it to other stuff. If you still remember, this is the shape function. Not remember, but just to show you that the beam structure, if later on we will derive that. As you can see, these are all the lines already. Your shape function is going to change. Alright, your N2, because of different magnitudes, you're going to change. But in fact, this is more in terms of the cube itself, because it's in terms of a polynomial, cubic polynomial. So the line itself isn't just a line anymore. It's more than just a line. So if you were to take a look, this is just polynomials. Alright, this is a third order polynomial because it's cubic. Alright, but for our case, if you remember, we actually derive things in terms of a first order polynomial, because it's x in terms of x. Alright, so therefore you can start to see the link between the beam and our stuff already. We use the first order to derive the bar, second order to derive I don't know what the hell, third order you will see that you're deriving your beam. Alright, so I don't know, just for you to see. Alright, but nonetheless, I may have a certain mistakes telling you that the integration of the line may be different like this, maybe other shapes like this, but I may be wrong. But just to inform you that you are still gonna integrate along this line. Alright, this line is this explanation over here right now is correct, but if it's in terms of the curvature, I am a bit unsure. So I'll leave you to think about it, but should be, I don't know. I'll leave you to think about it, but let's continue. So after explaining your line integral, let's explain the b. If you still remember, your b is equals to displacement, your displacement, what, strain displacement. Yeah, it's your strain displacement. B is your strain displacement. If it's in terms of a matrix, you're just in terms of a strain displacement matrix, which is like something like this. Okay, but anyway, let's just show you something. So you know that your b is equals to dn over dx. Alright, and we know that our shape functions is this one, right? We actually proved to you that we have n1 and n2 in the last video. Okay, so therefore we'll just simply sub it in. Alright, my n over here. Okay, how do I get this? Okay, you can rewrite this whole chunk over here as a matrix. This is nt, right? And this is your u2 and u1. Okay, so nt is equals to this form, so n is equals to this, like this. So just simply take this n, and I'll just visually bring all this in front of you. So I'll just simply plug it inside over here. Alright, where my n is. So I'll just simply plug n as this one. D over dx is simply here. I didn't move anything. Okay, so therefore it's simply this one. Okay, so I didn't cheat your feeling just now. Where am I? Never mind. So I think you get what I mean. So it's 1 minus xl. You can double confirm that what I sub in is the same as what you're seeing. Okay, it's over here. Alright, it's the same thing. Anyway, so now we're gonna differentiate this dude over here now. If I were to differentiate 1 divided by differentiate by x, you get 0. And minus 1 x over l, you differentiate, you have minus 1 over l. And you differentiate x over l, you have 1 over l. So I'll rearrange, I'll have minus 1 over l, 1 over l. Okay, so my b, this one can be my representation of my b. Okay, so I'll just sub in this thing into here and here. Okay, and therefore what I have, I'll just rearrange some stuff, so hold on a while. Okay, so therefore this thing over here we have proved to you as b, this thing over here I proved to you as bt, b transpose. And therefore what we can do next is to, we see that this is some constant. Alright, we'll just bring it up over there. We'll just bring this integration at the back. So what we have is this thing over here. Okay, now this thing over here, just to also remind you that this thing over here is a dyadic product. Dyadic means that it's an outer product. Let's say this is b, you know that this is b transpose, correct? If it's a bbt, if the t is outside, alright, rather than is btv where the t is inside, alright, this thing over here is called the inner product. This t over here tells you that it's an outer product, while outer is the dyadic by the symbol like this, and inner is just your dot product with a dot. Okay, so in such of the case that happens, bbt in our case is, well, I'm lagging, good job, it's something like this. You're gonna dyadic product your stuff. So if you're the dyadic product now, alright, what do we have is, so the dyadic product is simply taking this multiplied by this multiplied by this. Alright, so minus 1 over l, this one minus multiplied by this one, you will have 1 over l square. This one multiplied by this one, you have minus 1 over l square. And then this one multiply, you will have this matrix over here. Okay, now just simply paste the rest of the same stuff because it's just simply the stuff. Alright, and I'll evaluate this integral over here, because if you were to integrate in terms of dx, right, what you have is this thing over here is equals to x, right, from l to 0. Okay, so just simply sub in as this thing over here, since we know the integration is that already. Okay, so now we just simply sub in my x over here within the system. So what I have is this, alright, from l to 0, where x is from l to 0. I mean from 0 to l. So if x is equals to 0, this whole matrix will become 0. Alright, so therefore it's only simply l. You just sub in as l. So when you sub in as l, what we have for this matrix over here is, because it's l over l square, so we will have 1 over l, correct, for this case. Alright, so So likewise for other cases, so this is 1 over L. For other cases, if I submit L over here, so it's minus 1 over L. Okay, so because if I sub in X as L, alright, L and L cancel, we'll have 1 over L. Okay, same thing, minus 1 over L over here. So I think the rest you should know is the same style. Okay, if you don't understand what I mean, you just simply go back to just click a few minutes ago and then you just rewatch again. Alright, and then minus away, because when you sub in your x is equals to 0, so this is 0, this is 0, 0, 0. So what you have is all 0. At the end of the day, this is simply rubbish. It's just right, yeah. So what you have is only this, and that's all. Because minus 0 is simply getting back this matrix, nothing much. Okay, and then EA over L. I'm sorry, EA over here. Okay, alright. This word kind of like look like death. Alright, death in Chinese. But anyway, 1 over L lah. Okay, I don't know. But anyway, so I factorize out the L. Alright, I factorize out the L, so I have EA over L, and therefore I have this thing over here. Okay, so therefore you have derived your stiffness matrix all over like this. Okay, so therefore just to inform you that we have two milestones. Alright, the first milestone is to determine your shape function first. Alright, if you just take a look in the previous video, we derived your shape functions. Alright, the second milestone is to get a good equation that can represent your stiffness matrix K. Okay, so this is the good general equation. Alright, where it contains B. It is very powerful that you need to know that you need to have a equation that contains B, so that when you sub in, you have a certain shape functions together with it. Alright, so you're gonna utilize your shape functions that you derive and plug it into your B, and then solve for your whatever thing it is. It's just that the meaning of it all along is all what they're gonna do next is like this. Alright, so now derive the shape functions, we took on the approach of getting a first order system, and then you rearrange and stuff like that. Okay, so in the later part of this video, alright, we're gonna derive this thing. Alright, we're gonna keep on deriving this thing using the principle of virtual displacement. But before going into that, I'll just derive the stress. Alright, your stress for a bar. Okay, because normally if you're dealing with terms of the displacements, you're gonna deal with terms of the stress, the forces, everything. So in this case, in the next video, I'll just simply derive the stresses itself for a bar. Okay, so I hope that is pretty clear and give you a good perceptions of how in the later parts of the videos this is very useful, although that you may have some variations like this. Instead of E over here, you have EI, and then you have some other stuff over here. Okay, so I shall see you when I see you. So next video is talking about stress. Goodbye.